Okay, now that we've derived or formulated the equations based on one-dimensional flow, now we are going to look at how to formulate the equations for two-dimensional flow, which is the way we commonly solve the finite element method for seepage problems. And we use a combination of triangular and quadrilateral elements. And so this one's a little more complicated, so buckle up. Here we go. So for 2D flow, we subdivide the problem domain into a set of connecting triangular and quadrilateral elements. Now you can use all triangles if you want. In fact, that's probably the more common approach, but the point is you subdivide your problem domain into these two-dimensional elements, each of which has nodes at the corners and sometimes at the midpoints of the edges. And each of these elements is associated with a particular soil type, and that soil type can have its own material properties, hydraulic conductivity in the X and the Y direction. They can be equal, they can be different, and so the different soil types are represented here using the different colors. So how do you formulate the equations to solve this? Let's look at the different element types. The simplest element is a linear triangle. You have nodes at the corners shown by the red dots, and we assume that the head varies across that linear region, across that triangle using linear equations. So this would be the equation of a simple plane. If you can imagine, if you pick any direction here, it would be a nice linear variation. But that's the equation of a plane as it goes through that. So you can imagine if we had a mesh composed completely of triangles, and if we calculated the heads at the nodes, we're assuming that the head across the face of the element would vary linearly. So it's kind of like you're piecing together a series of linear tiles that form an approximation for the solution. And the smaller the elements, and the greater the number of elements, the more accurate that solution becomes. Another way to do this, instead of assuming that the head varies linearly across the face of the triangle, you can assume that it varies in the form of a quadratic surface. So now you add midpoints at the midpoints of the elements, and now the equation takes on x squared, xy, and y squared terms. So you have, in this case we had 3 coefficients, now we have 6 coefficients. It's a 6-node triangle. Likewise, for quadrilateral elements, you can have 4 nodes, and a linear quadrilateral is shown by this equation. It's not quite a plane, but if you go in any one direction, like between these nodes or between these nodes, it varies as a line, so it's kind of like a warped plane. And then again, you can do an 8-node quadrilateral or a 9-node quadrilateral, where you assume that the head varies across the face of the element using a quadratic surface. And so the advantage of a quadrilateral element is that they're more accurate. Using linear elements, you're assuming these flat surfaces, and that's, the head actually varies in a more continuous fashion. So the quadratic elements are more accurate and more efficient in terms of and when we say more efficient, we mean the degree of accuracy you get for a given number of elements. To get a certain level of accuracy with linear elements, you have to use more elements. However, some programs only support linear elements for the sake of simplicity. Linear finite element meshes are much easier to generate, and with modern computers, it's very easy to get plenty of elements to get whatever level of accuracy you want. So we don't see in seepage problems, you can often do both, but we often just use linear elements. And so you can compose your meshes using both triangular and quadrilateral elements, as was the case with the example I shown above. Again, quadrilateral elements, now I'm not talking quadratic versus linear, I mean quadrilateral versus triangles. Again, quadrilateral elements are a little more accurate. You often have to use some degree of triangular elements just for the sake of geometry to put it together at the edges. However, let me also say that when you're generating a finite element mesh, if it's all triangles, there are a number of really powerful automated mesh generation algorithms. And so they are frequently used. In this course, we're going to use the GMS software and SEEP2D. And all we have to do is define our boundaries of each material, and it's going to fill in the interior with triangles. And it happens almost instantaneously. It works beautifully. And so we often end up using just linear triangles. So, as we derive these equations, we're going to derive them based on linear triangles, partly because they're commonly used and partly because it's the simplest of all the different two-dimensional element types. So again, for a given element with 3 nodes, 1, 2, and 3, if we look at this in perspective mode, and again, we're solving for how the heads vary across that element. We're assuming that varies in a planar fashion across these elements. So H equals A1 plus A2x plus A3y. It's the equation of a plane. And we have 3 unknowns, A1, A2, and A3. So next we're going to develop a transmissibility matrix for the individual elements, similar to what we did for the 1D case, although it gets a little more complicated here. The next thing we do, step number 1 in developing the element matrix, is to relate gradients to heads. So if we take our equation for H, and you take the derivative of this equation with respect to x, we get A2. If we take the derivative with respect to y, we get A3. So it's just a simple derivative of a very simple linear equation. And so that's pretty easy, A2 and A3. And so also, if we using that equation, if we plug in the head and the coordinates at each of these corners, we get 3 sets of equations. So HI, the head at node I, is equal to A1 plus A2 times X1 plus A3 times Y1. And we do the same thing for node J and K. With these equations, so again, this set of 3 equations, we have 3 equations and 3 unknowns. We can solve those for A1, A2, and A3, and then plug that into our equation for I, and we end up with this result: I, the vector I, Ix and Iy, is equal to this matrix, which we'll show on the next slide, B, times these 3 heads. And so, by the way, this is a 2 by 1 matrix, and this is 3 by 1, and so B is a 2 by 3 matrix, and so that actually works out. So B is based on the geometry. This is just a function of the differences in y and the differences in x. But there's this coefficient out front, 1 over 2 delta, where delta is the area of the triangle, which is 1/2 xj minus xi times yk minus yi minus xi minus xk times yi minus yj, which we just calculate that once and plug it into here, and now we have our B matrix. And so we now have an expression for the hydraulic gradient expressed in terms of heads and element geometry. Okay, so this is our equation for the hydraulic gradient in terms of heads, and B is purely the element geometry. But we're not done. our next step is to relate the velocities to lumped flow through the nodes. Okay? Now, if we look at the midpoint of each of the three edges of the triangle, if we look at qxij, so that's the flow in this direction, it's equal to minus the velocity. Now we're putting a negative sign on the velocity in the x direction here because it's coming out of the element, minus vx times yj minus yi. So yj minus yi is the cross-sectional area through which the velocity in this direction flows. So it's basically saying the flow in this direction is the velocity in that direction times its cross-sectional area of flow, and we assume in the other direction it's a unit thickness. Likewise, qyij is equal to the velocity in this direction times xj minus xi, which is this width here. And likewise, if we do that for each of these 6 components, we get these 6 expressions for the flow in terms of velocity and the cross-sectional area through which it flows. Okay, so then we're going to lump the flow at the nodes. So qxi is going to be 1/2 xij plus 1/2 qxki. So what does that mean? So the flow in the x direction at node I is going to be equal to half of this flow plus half of this flow. Okay? That's what this represents. And so if you combine those terms, you end up with 1/2 Vx yk minus yi. And likewise, qyi, so this, the flow here in the y direction is 1/2 of this plus 1/2 of this, okay? So we add those up and we get this expression, and we continue to do that for all of these, and we get this matrix relating Q to V. So in a way, this matrix here is like an area term. So remember, the flow rate is equal to velocity times area. So this kind of represents the cross-sectional area of flow in matrix form. And now, if we do one other thing, if we define the flow rate at a particular node as the sum of x and y, we can basically collapse this. So these, we basically get rid of the zeros and everything collapsed down. So qxi plus qyi together equal qi. So we end up with just like a more compressed version of this. And so now, again, we have an equation for flow rates Q as a function of this geometry matrix here times velocity. So this is like an area matrix, another form of it. And notice, well, you may not notice it, but let me tell you that this matrix G is equal to minus delta times the transpose of B. And so therefore we can say Q is equal to minus delta B transpose times B. What is B? Well, remember, B was this equation right here that we derived when we were defining the an expression for the hydraulic gradient. So that's nice. We'll take advantage of that. And then finally, we are going to relate velocities to gradients, and we do that using Darcy's law. V is equal to Ki. So this is just our standard two-dimensional Darcy's law equation. Vx is equal to minus Kx times Ix minus Kxy times Iy. And that gives us V equals Ki. So now we have 3 equations, 1, 2, and 3. This one defines the hydraulic gradient in terms of heads and geometry. Q is equal to this times A. This is kind of like saying Q is equal to VA. This term here kind of represents the area of flow. And then this one is V equals Ki. That's just Darcy's law. So the first thing we do is we have this equation for I, so we're going to substitute that down right into here. And now we have V is equal to minus KB times H. Then we're going to take this term and we're going to plug it right here. So we plug that in, and now we have an expression for Q is equal to all of this times H, and really this here, the delta and the B are all based on the triangle geometry, which is a function of the area of flow and the distance of flow, and then K is the hydraulic conductivity. And so that then combines into what we call the transmissibility matrix, like we saw before, or T is equal to, you know, delta B transpose K times B. So those may look complicated, but you write a function or a subroutine that formulates that one element at a time, and it's actually, you end up with if it's a 3-node triangle, you end up with this equation T is 3 rows and 3 columns, and it has a bunch of constants in it. And then essentially you add those, you start with a zero matrix and add those in like we did in the 1D equation, and you can formulate the whole equation. So it's a little more complicated, but not terrible. And it's certainly something you can code up, and you end up with a set of equations, which you then have to apply boundary conditions and solve, just like we did before. Yeah, and that's what I was talking about here. T is a function of geometry and hydraulic conductivity, and we formulate that and solve it, apply boundary conditions and solve it. So that's basically how you do the 2D finite element method. All right, so once you've got that, you have a series of equations you solve. Now, the last thing we want to talk about is mesh design. And so the finite element solution is an approximate solution. The denser the mesh, or the larger the number of triangles, the more accurate the solution. So to improve our accuracy, we use more elements. How do you know how many elements are enough? Well, there is a systematic way to do that, but generally just make your mesh pretty dense and you'll be fine. You know, modern software is so fast and so easy to use and has such high memory capacity for seepage problems. We can very easily have enough elements to solve it. Like if we were solving some sort of three-dimensional, super complicated stress or flow analysis, you'd have a lot of elements. You know, maybe like in groundwater problems where we have three-dimensional elements, you could get maybe 500,000 or 1 million elements. But in 2D seepage problems, I promise you will not ever get into a case where you have too many elements to solve. So let's look at our classic sheet pile problem that we've looked at before. And once again, this is symmetric. So we can either mesh the entire thing or we can mesh half of it and solve it, and then the solution is symmetric. For the purpose of these slides, I'm going to only mesh half of it, but in reality, if I were doing this in a program like Seep2D, I'd just mesh the whole thing because it's easy to do. And so if we're just looking at one side, you could theoretically use a set of coarse, we call this a coarse mesh because that's, for the problem domain, that's not very many elements. In this case, the problem domain is rectangular, and so using quadrilateral elements works really well. Very easy to set up. This would be a more dense mesh. I'm not saying this is necessarily sufficiently dense, but this would give us a more accurate solution. Now the problem is most of our flow is going to occur right around the tip of this sheet pile. So we're going to have big changes in head over a short distance. And in general, you want your smallest elements to be concentrated where your flow is the greatest. And so one of the beautiful things about a triangular mesh is it's very easy to adjust the mesh density where right here where you have where most of your flow occurs, and then you can use larger elements over here where you don't need as much accuracy. And so that's one of the benefits of using an unstructured mesh, is you can refine your mesh to be much more dense where you need it, and leave it coarse where you don't need the accuracy. And again, this is all really easy to do with our modern finite element software. All right, so that's how we build meshes and formulate our two-dimensional finite element equations.